review to get, like I said, to get ourselves back in the zone. Let's review what we did last time just to kind of, oh no. Come on, little guy. You can do it. There it is. Okay. Okay. One that we both know nothing about and know everything about all in the same moment. We know that it exists. We know how to study it. We don't know why yet. And that's what we're really trying to figure out. That's what scientists are working on. We also talked about these other ones. After we did that, then, so are our brains kind of remembering this now? Okay, it's been a few days since we were together. We talked about the frog on the table. We drew a three-body diagram. The three-body diagram is one object and the forces acting on that object. Okay? And the three-body diagram is super exciting. We have those two forces acting on the frog. We have the table pulling up on the frog. We have the pulling down on the frog. And you told me that the total force of the force on this frog is okay? Pushing their out. So it's net force. Then we got the bowling ball out. And that was fun too. We had 4 different pieces for the bowling ball. This is the stuff whiteboards actually works good, right? What did we notice about A? The ball is still and C, the ball. What did we notice about that? That's the forces, right? Yeah. You can't. Exactly. Exactly. You can't tell if it's moving or if it's that's huge. Like if you write that down in your notes again, I would. Okay. Or maybe circle it. Put big stars by it. That's a big deal. You cannot distinguish between a velocity of 0 and constant velocity. The thing you know is that it's not what? Accelerating. In this case, I was pushing on it, right? I was accelerating it. You know that because of one extra. Does that make sense? And over here, you know that it's accelerating. It got stopped, right? Slowing down. Okay. We have just figured out these two things. Without really, I mean, this is not hard, right? We didn't like anything crazy. We have figured out what most people will call new science. Okay, so I'm going to tell you right now, Isaac Newton is not my. Isaac Newton is not a very nice, really smart. Okay, he was very, very smart. But he was very in elementary like the character, okay? Not be the most talented. He gets credit for these laws. Newton's them out without calling them that, right? I'm going to tell you what they are, and I'll show you that this was the whole of long people, boulders, yes, and cables too, yes. And this is not a surprise. Newton did write it down in a nice way, but make it. I just really want to make that clear. We'll call them Newton's laws, but let's be honest. Just copycat. Okay. Here's my version. And I don't want you ever, and hopefully never to write you to know. If F net equals 0, if F net equals 0, well, let's look at situations where F net equals 0. Like in A and C. Is the object accelerating? No. Okay. If F net equals 0, then acceleration equals 0. We got that, right? The other option, if it doesn't, if this isn't the case, then we can say that F net doesn't equal 0, right? If F net doesn't equal 0, then what? Good reasoning. Yeah. Is that okay? Really Newton's first and second laws. That's really all. This is not hard. Do you agree? This is pretty straightforward. This is really what you need to know. If F acceleration is 0, that's easy. Okay? If F isn't 0, acceleration isn't 0. That's easy too. Now there's one other little bit to it that we do want to add, because just saying something isn't 0 isn't very. So we might define maybe what it is. Let's talk about acceleration. To accelerate means to do what? Change velocity. Who else with us? Besides somebody said. Go slower or go faster. Change or change direction, right? Or direction. If there is acceleration, if it's going to work backwards, if there's acceleration, what do you know about the net force acting? It's not, there has to be some force, right? So let's talk about these forces. I sent my bowling ball back down to the cross community to get it back. We're going to imagine a bowling ball here. And I also need to imagine there's a beach ball. No. I lied. I want to do bowling ball and bowling ball. Inside. Okay? Now, I can take one bowling ball and I can push it a little bit. Or I can take one ball and I can push it really, really hard. Like, what am I changing there? So I'm changing something that's changing the acceleration. Do you agree? What is it that I'm changing that changes the acceleration? The force, right? The bigger the force, the what? Is that logical? Does that make sense? You guys aren't as smart. I want to say that if the net force, and this is the overall net force, right? Add them together. If the net force is bigger, the acceleration is also going to be bigger. That's logical. That's logical, I think. Now we'll take my other, so I'm going to take a bowling ball and I'll take a beach ball. Now, in that case, what am I changing? What's the difference between a bowling ball and, yeah, the math, right? A little bit, a little bowling ball, right? If I use the same kind of force to push the bowling ball or to push the beach ball, are they going to move the same? No, you know it. What's going to happen? Which thing? We're going to assume it's inflated. But even if it's not inflated, it might not roll, but it would definitely accelerate. Do you agree? Yeah. So it's definitely accelerate more. So let's write this down in a similar way. If I have an increase in mass, what's going to happen to my acceleration? Think about it carefully before you answer. It's going to go down, right? So people versus bowling ball, right? Low. Is that okay? These are logical. It doesn't take a genius to figure that out. We can all do it too. I'm putting two things together because I don't want to just have like little ratios. I want to have an answer. Everything just not equal zero. I want to know something. The acceleration, well, these are proportional, right? One goes up, the other goes up by the same amount. So I'm going to put in my relations, I'm going to put F net up here because it's like they're not equal, but they're equal with some sort of other piece in there. As one goes up, the other goes up. As mass goes up, the acceleration goes down, or as mass goes down, the acceleration goes up. So I'm going to put that in the denominator. That makes sense? I would rather have half of a pie than a third of a pie. The 2 is bigger, or so the 2 is smaller, but the half is bigger. Does that make sense? Yeah? Fractions are funny that way. So as n goes up, a goes down, or as n goes down, a goes up. Is that okay? There we go. That's the other thing you just put a circle around. It's a, I wouldn't even call it because it doesn't have, it's got rounded corners. It is a containment field. Call it what you will, put some orientation around it to the keyboards. Okay. Now, you know what we're going to call the second law. You may have noticed it when they put how many laws. I agree, or I argue with the same thing. This is here. The third law is totally separate. It's way more important. We're going to do it later, so we're not bogging down because you can do this just like separately. So we're just going to focus on these two right now. Questions yet? Are we happy? So, it sounds pretty straightforward. But really, it's all. So, we mentioned when we were together last time with the frog on the table that the earth ball on the frog has gravity. The table on the frog thing has a special name that goes with it as well. The name that goes with it, it's kind of a fun name. This thing is called a normal. Now, sometimes people read the word normal, and when they say normal, they think regular, unexciting. That's not what this normal is. There's a mathematical term or normal is a mathematical term as well. Anybody ever heard the term normal in a mathematical context?
Isn't it like, I can't remember, but does it have to do with like the subscale thing with the
Yes. Is that act to okay. Whenever you have a surface, you can include a normal force, and it's always going to go perpendicular. So it's really easy to figure out how to draw it. Does that make sense? We're going to talk more about the normal force in a minute, but I don't want to tell you too much right away, otherwise it seems kind of overwhelming. So we're going to do a few problems here, 3 of them, in fact. Okay. This says, can you guys see that in the back? Is it kind of little? Is it okay? You let me know. I can make it bigger. Always let me know if there's something you can. This first one says determine the normal force, right? Of the frog are acting on the frog on a table. So we're actually first thing that I want you to do, and it's set it up here, but I zoomed it out, is to draw an SBD, SBD,
free body diagram.
free body diagram, and is to draw a free body diagram to look one thing. I want to do it. So I'm okay. That free body diagram. Each of the forces needs to be linked with how many objects? Something on front. Something on front. Object. Okay. Once you've got your free body diagram, check it. See if you can look at it. Okay. All right. Yeah. What was one of the forces in your free body diagram? Force of the earth. Where did that one go? Down. Something like that. Down. In parentheses, I can write down that that's a what kind of force? Gravitational. So I want you to get in the habit of writing them every time. Every time. Every time. Every time? What other forces did you have? Where'd that one go? And not only does it go up, you know it's up because it's what to the surface? The force of the table. Mine? I know, right? And in parentheses, I'm gonna write down, so I don't forget, this is a what kind of force? Say it like that. That's what I thought you meant. Okay, let's get to that. Then we're gonna write down an net equation. And net means what? Net force means all of them added together. So this factor is different than you consider, and you went to your equation and you said, we can fix all of these variables. You know what I'm talking about? We don't do that. We're going to make our equation based on our picture we draw. Okay? So I'm going to look at this and tell me what to write down. So here we go. F net equals, well, let's write them all down. I've got an FG and an FN. So I'm going to write FN plus FG. I'm going to ask myself, so, is the frog accelerating? No. And yourself says no. So that means that F net must be equal to 0. So you can either just say 0 or you want to have it. You can write this as NA because I don't know if you noticed that, but that's really what the contour next to be. If you move the M over here, then F net equals NA. Okay? So you can write it either way. But I'm going to say, oh, I'm just going to see where stresses. Now, they want to know what the normal force is. I don't know what the normal force is yet. But I do know something about gravity. The force of gravity can be calculated. The force of gravity is also known as the what of an object? The weight. Does that make sense? Force of gravity is also known, I'm going to write a couple things down here, as the weight of the object. And what is the weight of an object dependent on? Its mass and gravity. What gravity? The Earth's gravity, the force or the, you know, it's dependent on the mass and the acceleration. That was an A. What was it? Acceleration. Acceleration. Okay. And the reason that I want you to differentiate between the two is that the force and the acceleration are different. Okay. Fg, you told me, is dependent on the mass and is dependent on the acceleration of the gravity. So the weight of an object will be different if it has a different mass, right? I have a different weight than does the frog. Are you taking me? The frog is not one of us. We're both. Accelerate faster. Who's going to accelerate faster, the frog or me? What's going to accelerate faster in a vacuum? A feather or a hammer? What's going to accelerate faster, the frog or the hammer? Neither. What's going to accelerate faster, the frog? Neither, right? Always the same acceleration, yes? And that's why I want you to be really careful when you say the gravity, like what gravity? Acceleration due to gravity? Okay? The acceleration is the same for everything. The force is different. So, if I know this, can I find the weight or the on the frog? Yeah. And if I know that, check this out. Fn is going which way? Down. Fn? Back up. Up. Fg is going which way? Down. Down. So I'm going to subtract. Is that okay? Those equal to 0? Oh, wait. That just means that Fn is equal to the mass. Oh, okay. The weight is defined as the mass. I'm going to put in a box or a circle or some sort of indicator that it's important. Okay. So can you find the normal force now? Yeah. Yeah. Go ahead and do that. We've already taken the negative into account. So when we multiply here, we're going to multiply by positive 9.8. We've already taken the negative. So this is positive. don't have a calculator out yet, get one out. How's it going? Multiplication fun? With your 4.4. Whoa. Whoa. All right. Number for the value. Okay, so then the next question was what?
What do we do for unit?
Well, let's figure out what we're going to do for you. Kilograms times meter per second squared. And you could leave it like that. And that would be fine. Kind of a lot of stuff to write, huh? So, we can use another unit, find unit that takes all this stuff out. And my favorite. Sorry. Okay. Rising Newton is the one that gets the name unit. Okay. 1 Newton is equal to 1 kilogram meter per second squared. So instead of writing kilogram meter per second squared, or I'm going to write 4.4 newtons. Okay. Forces are measured in newtons. Forces are measured. Okay. All right. So here's the weird thing. So we've done 2 forces so far. I'm going to list them on a new piece of, or a new sheet. You may want to list them. Forces we know. We said gravity. Which really is, well, remember we said it has the object, the forces in 2 objects. The force of gravity, just what we're talking about, is the force of what on our object? Exactly. So I'm just going to put that in parentheses. So it's the force of the earth on your object. It's also known as weight, but generally I want you to call it the force of gravity or the gravitational force. Okay? And so I'm just kind of writing this down so we can kind of keep them organized. And Fg we can calculate is equal to mg. You'll notice again that I keep writing these little of force, right? And on top of the acceleration, because that direction really matters. Okay, you really take. Let's take a look at the direction. Where is the direction of the acceleration of gravity going to go? Down, always down, right? Center of the earth. So the force of gravity is always going to go where? Down towards the center of the earth. They're in the same direction. So I'm going to put that on here too, just so we keep that in mind. Okay. This is going to go towards the center of the Earth. Okay. Life is good? What's the other force we know about already? The normal force. Fn. And this is the force of what on the object? The surface! Yeah. So that could be the table, or the floor, or the hand, whatever. Okay. What did you say? Cake? Yes. I'm not opposed to cake being in problems. Okay. Sure. Okay. Now, unlike the gravitational force, the normal force doesn't have an equation that goes with it. Let me tell you what we do know about the normal force. We know that it always is perpendicular to the surface. Are you all okay with me writing like this? Yeah. You know what that means, yeah? Okay. Now, the normal force is funny because the normal force is only going to push as hard as it needs. I'm sure you all don't know what that is. It just pushes you to, okay? Okay? Never, that's not really. So, let me give you an example that might help you to envision the normal behind this only doing as much as I had an experience this summer. I don't know, you probably started having experiences kind of mode where you look around the world, oh my gosh, there's everything. I will tell you when I was experiencing this summer, I was now this sounds emptying the dishwasher is physics, right? So my husband and I were emptying the dishwasher, and for whatever reason, usually it's just one of us, but for whatever reason, both of us were emptying the dishwasher. He was taking plates out of the dishwasher and handing them to me, and I'm going to take a stack and put them in the cup. Yes, can you picture this? And I have so I'm going to put the plate on my hand. Yes? So the surface is my hand. If you just draw my diagram of the plate sitting on my hand, you have gravity pulling down, and my do you agree? Okay. And assuming that I'm not moving, are the plates accelerating? No. It means that the net force is zero. So my hands are as the earth is down. Everybody see that? So now feel. Put another plate on top. If I was pushing exactly the same amount of force the whole time, before and after that second plate I put there, would those plates sit there? No, where would they go? Right? Yes. Yes? Okay. But that doesn't happen because what do my arms do instinctively? They're going to apply more force. Not much more. The force times the mass of the plates. Yes. Or how do you compare that to one plate? Right. And they put another one on there, and that feels like every time I was like, I was that makes sense. So here's what I'm saying. So the more places I have, yes, okay. Now, there may be a point at which, if they just keep stacking plates forever, that I may at some point not be able to handle it. Be a break. There you go. Now the acting is big here. I take it off, and I'm going to take it off table. It's not like you need to do something. You agree? And now only that you need to be in. Okay? It needs to so this. So that's the deal with the normal. There isn't an equation. There's no equation given for Fn. We just know if I were you, I would leave some space below this because we're going to add some more forces to this in a little bit. We're going to go back and do another normal force problem now. Okay. You guys are going to love this one. I just know it. I'm going to take the frog on a walk. So here's the frog handle on. Okay. Here's the frog. And the spring is lit. Okay. Then this would be the exact same frog we just. And the normal force. What was it? Not do. Net force. So now we have with N words, right? You got the net force, and the net force on it is the normal force on it. 4.4 newtons, right? On a wall. So happy.
I already asked that question.
Now, you got what? Force of the This is how I work. I'm going to add one more force here right now. The force of tension. Tension force always causes people to guess. Now maybe it's just. All right. Good. I'm glad you think so. I'll tell you, I go home some nights and I tell my husband I told him really because you're great. I'm glad that you said look, they said all right.
Alex said no.
Right. Tension force really all it is an applied force. My hand. Really all we're talking about force is just a transfer of an applied force through a string. The cool thing about tension is that it can actually change the direction. But we're not going to get through it. I just need to know. I should write down that in A is applied force. So that would be like when we're doing with the volleyball, the force of the force on the ball and the force of right on the ball. Remember that? That's the right. Either or a contact. So that's what we're going to say. This is the force of the string on the frog. We'll see. Okay. And then the applied force is generally the person or something else. And that one will either always be given or there's no. Okay, so back to the problems. The walking frog problem. Determine the normal force acting on the frog, same frog, who is being walked along a horizontal surface with an applied force of 2 newtons, at an angle of 65 degrees relative to the horizontal. Well, it's a good thing that we did because we know how to deal with angles, right? We know how to deal with forces at angles. Let's draw ourselves a picture. We're going to start with a 3-body diagram every time because that 3-body diagram is going to tell us our equation. You already listed out the forces. What forces did you say were acting on the frog? The force of the string, and that's going up at 65 degrees relative to the horizontal. Something I'm going to string on frog, and I'm 65 degrees. Is that okay with everybody? What else do I have? Force of the floor. Which way does the floor go? Up, pushing upwards, perpendicular to the surface. Is that okay? And that's a normal force. I'm going to put F sub n there. And next to that force of string, I'm going to put F sub t for tension force. So don't forget that. And what else do I have? What's that? Gravity. Or the force of the earth. So far, so good. Is that okay? Now, without even doing any math or any, actual calculations, thinking back to like the plates in my hand problem, is the normal force going to be greater than, less than, or equal to 4.4? I want you to think about it. Is the normal force going to be greater than, less than, or equal to 4.4? Back to case. Back to case. I come up with a reason. All right, can we vote? Greater than the normal force. Correct. This is going to be less than 4. Equal to 4. Okay. Well, since the force of gravity is always constant, and normal can vary as much or only as much as it needs. Yep. But then the spring, it also gives some force, so maybe a little less. You're exactly. This force is 60, this force potential is 65 degrees. We can component like we did in last. If we do that, let's try that out. Let's see if we can ourselves that in over, and then we can go. Is that okay? Do you do there? Okay. And this, make sure I'm what you said. This thing plus this thing equal. Does that make sense to you guys? These two added together have to equal this. Let's write down F net equation sort of way. F net. We're only worrying about the net direction, right? The y direction, the up and down direction. So all I'm going to write down is this y. It's kind of like motion. What forces are acting in the Earth on the frog? G. What else you got? What else you got? The floor on the frog. FN. What else? What else? What else? Andy. The string, is it all of the string force? It's only the y force. We call that FT sub y. Those three forces added together have to equal what? Because it's not what? Accelerate. It could be moving up or down, but it's not accelerating. That's the key, right? The it doesn't say that it doesn't say that it's moving at constant speed, but if it's moving at constant speed or not, which direction is it moving in that only the horizontal? It's definitely not accelerating in the vertical direction. Does that make sense? That's a really good question because so in the y direction, the acceleration is 0. Can you finish this from here? Do you think you can do it? I think you can do it. I want you to work with your table mates. I'll write things down too, but I want you to give it a shot. The normal force given this information. Give it a try. Hmm. Hmm. somebody's gonna yell at you. How's it going? Are we okay? Yeah? What are we getting an answer? Did you get it? Or are you sure? Bridget has a question. I don't think you know how long it's too long. That makes sense. So, like, can you talk to me about this one? Okay. Okay. I just wrote down. I feel like if I just walk you through it, I do want you to know the process. Okay? This is and then it's up to you to help you. But it doesn't mean that now you want you wrote this one down together. After we write it down, the next as G is going down, okay, as it's going up, so it's positive, going up, so Fn equals 2.1 newtons. How you doing? Were we right about the normal force? It is definitely less than it was for the first one, right? Good. Oh, really? Why are you turning off? Thank you. Come back in a moment. Okay. Now I want to answer what you said earlier. Now, here's my question. Now I want to look at we're going to do two problems that aren't actually written on here, but we're going to write them down because we can. Here we go. I would like to know, so we're going to put, this is an if situation. If there is no what? What was it that we had to leave out? Not acceleration, but when that little clock was rolling, and I told you to ignore something. Yeah. So what is it? If there's no friction, because I talked about it. Okay. If there's no friction, I want to know what the acceleration of the frog is. Okay. Would you agree with me that if there's no friction, then the frog is accelerating? Then this looks a lot like the bowling ball either when it's pushing it or when it's stuck. So how do we figure out what the acceleration is? Any idea? Bridget, what you got? So that would give you the that would give you the 9.8. Does that make sense? You're kind of on the right track, but let me ask this question. What direction is it going to accelerate in? In the x direction. Does gravity act in the x direction? No. What were you going to say?
We can take the
Okay.
and then
Okay. So that's kind of I want to make it so that when the problems get harder, we will formal. So after we just the net force stuff. And it's going to get us to the point take us. We know how to do it. In the x direction, acting this is a little part of the story, right? All of this, no, it's really the x part of the string. So ft sub x. Are there any other forces acting in the x direction? So then we're going to say that equals ma because we're pretty sure that it's accelerating because there's only one force. If you have one force acting on something, it has to be accelerating, right? It has to be. So I'm going to put a little h of x there. And then that you can figure out its acceleration. What's it there? I don't remember, but we can look. 0.45 kilograms. And the force was 2.5 newtons at an angle of 65 degrees. The mass is 0.45 kilograms. And the tension force was 2.5 newtons at 65 degrees. So talk to your table mates. Help each other out. See if you can figure out what that acceleration is. Because the net force is always, if the acceleration is not zero, the acceleration is always equal to the force of the momentum. Remember we did that before? So it's the same deal. That's where that comes from. Good question. How's it going? What are we doing over here? Is it okay? How are we doing over here? Yes. We have like 10 minutes. 2.4, something like that. 2.2. Can we double check divided by a kilogram? You ready? Okay. This one is going to turn things to an angle. So far, our little frog has sat on the table, floor, both of which are flat. But is every single flat? No! And valleys and mountains and exist. And we want to know about the normal charge the first time we try it out. So here's the problem right here. I mean, not like the problem, but this is the question that we're asking. We have a ramp, 25-degree incline. We want to draw a free body diagram. We're going to talk about the normal force in a minute. I would encourage you to make it at least like 4 lines high and like half of the degree. Trust me, it will make your life better. Okay? So here we go. Here's my. Then I'm going to put my frog on the ramp. And then we're going to write down the forces acting. So, what forces are acting on my frog? Raise your hand. Force acting on my frog. Go, Tanner. Earth. Which way does that go? Down. Always down, right? Center to center, straight towards the center of the earth. So don't be tempted to draw it like this. Is that straight down? No. Straight down. I want you to draw that force really long. Again, because I know what's coming, and it will be to your advantage. Okay? So I'm going to write the F of the earth on the frog in parentheses FG. Fantastic. Are there other forces acting on the frog? What's that? Oh, yes. What force would you like to talk about? The binder force. Binder force. Yeah. What is it? What kind of force? Normal. Yes. Normal. Normal. That's what I like. Normal. Normal. Oh, normal means always going which direction? Yes, I love it. Perpendicular to the surface. So here's the deal. We have to draw perpendicular to the surface. Unlike the other times when the normal force is like this normal force doesn't go like that, right? That's not perpendicular. We need to make it perpendicular to the surface. So it's going to go like this. Interesting. Ha ha ha. Now, we're going to write the force of the binder on the frog. And in parentheses, I'm going to say N. Now, if these are the only two forces acting on it, what's going to happen? Upside down. Because if there's no friction, there's nothing else acting. If we look at these forces, they're both pulling kind of in the general direction, right? So absolutely, on the ramp. But I think it says the problem. If it doesn't, it should. Yeah. Well, sitting on the ramp. Well, sitting on the ramp. That implies there has to be something else acting. And that's that mysterious force that we haven't talked about. But we're going to name it what? Friction. Whoa, hi. Right? Okay. Where does friction act? What is friction? Almost like a philosophical question, right? My fifth grade teacher did that when she talked about friction. Friction. I was like, why does your fifth grade teacher ever did that to you? Why? What is it? Why? What is it? Say that loud. Yeah, two objects moving, like two objects moving or sliding relative to one another. Okay? So two surfaces in contact produce friction. We're going to write that definition down in our list of forces. Right, so that's why we left some space in the forces we know section. Friction, FF. So this is when we have two forces that are interacting be the force of the surface on the object. Okay. Somebody's going to look a little bit up in their list and notice what? The what? Right. We've also got it here, right? What else? Normal force. Normal force is force of an object, and it's always what? Yeah. Or excuse me, surface. Always perpendicular to the surface. The frictional force is always going to be the opposite of perpendicular, would be parallel. So this will always acts perpendicular, excuse me, not perpendicular, wrong, parallel to the surface. And even more information for you, it always opposes motion. Oh, thanks. Okay? Always acts parallel to the surface, always opposes motion. Okay? We're going to talk more about that next time, but that's all we need to know for right now. So you're going to leave some space below there too, because you're leaving space by everything. So if I was going to write a frictional force, where would it go? Parallel to the surface. Up or down the ramp? Up, because the frog otherwise would go which way? Down. So it's going to go up the ramp. So this is going to say force of the surface. I guess that's what it said. On the frog. But in parentheses, okay. Now, your full attention for the next minute. Can you do it? 4 minutes. I want to find the normal force. I want to find the normal force. Right now, I've got 3 forces acting. Are they all perpendicular to one another? No. Now, on the one that I did before, on the problem I did before, do you remember I broke this force up into X and Y pieces? Yes? I'm going to do the same kind of thing, but I'm going to ask Lizzie, if you had a choice to either break one force up into 2 pieces or to break 2 forces up into 2 pieces, which one would you pick? The easy or the hard one? Easy one, right? Which is going to be easier, to break 2 things up or break 1 thing up? One thing. These 2 are already perpendicular, yes? So let's just break this one. Are you with me here? Okay, here we go. This is important. Stay with me. Part of it's going to be perpendicular to the surface. That's FG perpendicular to the surface. Is that okay? The other part's going to be what? Are you okay? So far? So far? So if the frog is not moving, FG parallel to the surface and FF are going to be equal. Does that make sense? If it's not sliding down the ramp. If he's sitting still, Fn has to be equal to what? These guys will have to be. Okay? We're almost there. I had a few of you in geometry. I knew you were some geometry. I just this online. Andy? All right. We know this angle, right? 45 degrees. I'm just going to call it theta. Okay? And if I add up all of the angles in a triangle, how many that up to? 180. You all know that, right? Okay? If this one is 90, then these 2 have to add up to what? 90, right? So I'm going to call this one here 90 minus theta. Is that okay with everybody?
Yeah.
So far, so good? Now, new color, more fun. All right. This thing says perpendicular. Do you agree? Which means that means that these guys are perpendicular. Now, Lizzie, if I add up all of the angles of what do I have to add? 180. You guys agree? Now, if I add up 90 plus 90 minus theta plus that, what does this have to be? A lot of weirdness. 90 plus 90 minus theta plus that, what does this have to be? It has to be theta. What? What are we talking about? Oh my gosh! This angle right here and this angle right here are the same. That's gonna make your life finish that next time.